Hi, hello, welcome. This is Discrete Mathematics, and today we're talking about section 3.2, sequences and strings. A sequence is a function where the domain is often the set of natural numbers, although it doesn't have to be. Our book often denotes natural numbers as z plus, so that would be positive integers. It can also be considered an ordered listing of numbers. So a key thing here is that it is ordered. So a sequence, formal definition here. A sub n is an ordered list of numbers of the form set notation a sub 1, a sub 2, a sub 3, all the way up to a sub n, and it can continue on. It is also a function whose domain is a subset of the integers. N is called the index of the sequence, which indicates which term we're talking about. So this right here would be the second term. A sub 17 would be the 17th term in the sequence. And that matters because the ordering of a sequence matters. If D is a finite set, the sequence is finite. If D is infinite, then the sequence is infinite. So you can have a set of 7 numbers. You can have a set of an infinite numbers. We use a sub n to denote the whole set on the domain. A sub n denotes a specific element in the set. So here we've got the set of all of your a sub n's, and then here is a particular element of that set. So before we get into this, we're going to talk about some differences. I want to note a few differences, and I've said a couple of these already. Differences from sets. One of them is that order matters. In a set, the order doesn't matter. And the other one is that repeats are allowed. We're going to see that down below. So in sets, the order of things doesn't matter, and you're not allowed any repeats. And here with our sequences, we are allowed both of those things. Okay, we are ready for example 1. Consider the sequence defined by b sub n, which is 2n plus n squared, where negative 2 is less than or equal to n is less than or equal to 1. What is the sequence, and what are some ways we can write the sequence? So these are our indexes, or indices. Is that how you spell indexes? I guess I should have looked that up before this video. Oh well, we're going to go with it. And that is negative 2, negative 1, 0, 1, and 2. So I want to know, this sequence has 5 terms in it. I want to know, what are those terms? So let's go ahead and figure those out. Here's my index, and here is my value of the sequence at that index. Negative 2, negative 1, 0, 1, and 2. So we are going to plug in our index into our sequence formula. This is 2 times negative 2 plus negative 2 squared, and that is going to be 0. 2 times negative 1 plus negative 1 squared, that is going to be negative 2 plus what is negative 1, and we can keep going. This in is 0. This in is 2 times 1 plus 1 is 3. 2 times 2 plus 2 squared is 8. So those are our values. I could write the sequence just with those values in set notation. So B sub n is the set that contains 0, negative 1, 0, 3, and 8. So notice here the order matters, so I cannot change the order. And also I have 2 zeros, and that's fine because order matters, repeats allowed. Another ways I could write my sequence is I could write it with set notation, b sub n, where n goes from negative 2 to positive 2. Or I could sub b sub n for 2n plus n squared, where n goes from negative 2 to 2. So this is 3 different ways I can write my set. They all have a certain utility, and we'll see in the coming examples why you would want to have the sequence be in one form or another. Okay, so we've got 4 different ways to describe our sets. A sequence can be decreasing. If for every I and j elements of D, if I is less than j, then S sub I is greater than S sub j. So this is saying that as I'm moving from element to element, the element that I have right now is smaller than the next one. So that means that my sequence is increasing. So an example of an increasing set, my current element is greater than the one that came before it. So my sequence is actually decreasing. Sorry, I drew my arrow the wrong way. So a decreasing sequence would be something like 3, 2, and then maybe I'll go to 0. It doesn't have to necessarily go exactly in order. Like it doesn't have to be they don't have to be consecutive integers, but they just have to be getting smaller. That's decreasing. Sequence is increasing if for every I in j, if I is less than j, then s sub I is less than s sub j. So that means the next element is bigger than my current one. That is an increasing set. So, an increasing sequence rather. So example of something that would be increasing would be like 1, 7, and then 9. That would be increasing. Next one, a sequence is non-increasing if for every I in j and d, if I is less than j, then s sub I is greater than or equal to j. So here we're allowing this or equal, which means, so this is not increasing. It's not increasing anywhere, but it could be decreasing or it could be constant. So we could see constant. Oh, whoops, I held my pen for too long. It could be constant or it could be decreasing, either one of those. So here in these two, spoilers, the next one also, we are allowing repeats. And these first two, there are no repeats. Because if you are repeating, then I'm not strictly greater than or strictly less than. So an example of something that would be non-increasing is something like 3, 3, 2. So here I'm not strictly decreasing because I've got something that's the same, but I'm also not increasing anywhere. So this is a non-increasing function. It's sort of like decreasing plus constant is what non-increasing is like. And that brings us to our last one, which you can probably guess, and that is non-decreasing. And that is like increasing plus constant. So it could be increasing or it could be constant. So something like 1, 7, and then another 7, and then maybe a 9. So this is kind of increases and then stays constant and then increases some more. So that is not decreasing anywhere, but it's not strictly increasing because we do have that bit of constant in there. 4 ways to describe a sequence. I think you have a couple of homework problems. Well, I think this is like an entire problem is it decreasing? And then the next one is it increasing? And then is it not increasing? So it feels like a lot. It feels like 4 problems, but really it's kind of one idea altogether. So you have a couple of chunks of your homework that ask these 4 questions. So you can look forward to that. Example 1, revisited. I want to tell whether the sequence is increasing, decreasing, non-increasing, and or non-decreasing. It could be multiple of these, but it can't be all of them. Like it can't be increasing and decreasing. But it could be increasing. We'll just see. We'll just see what it is. Let's see. Our sequence, I'm going to write it down again, was 1, -1, 0, 3, and 8. So let's see, from 0 to 1, -1, it goes down, and then it goes back up, and then it goes up, and then it goes up. So this is actually none of these. Sad face. Maybe we'll do another just example kind of off to the side. Something like, I don't want to use purple. Maybe I'll use this one. Actually, I do want to use purple. Change my mind. Something like 1, 7, and 9. This is increasing, but it is also non-decreasing. So every increasing sequence is also non-decreasing. And same thing with every decreasing sequence is also non-increasing. So it's kind of like every square is actually a rectangle type situation. So that we see that here. But this example that we saw in example 1, that sequence in example 1 is none of them. Okay, here we go. Definition. Let S be a sequence. A subsequence of S is a sequence obtained from S by choosing certain terms in X in the same order. So I'm choosing certain terms, and then I'm also keeping the order the same. So 2 things that have to happen. Same items, same order. If we let n sub 1, n sub 2, n sub 3 are all the indexes of the subsequence S, then the set of S sub n sub k would denote the subsequence of S. Let's look at some examples of subsequences. Let S be the sequence A, B, C, F, F, Y. Let R be the sequence A, C, F, Y. And let T be the sequence B, A, Y. R, R, and T subsequences of S. So I'm looking for, let's look at R first. So for R, let's see, I've got A, C, F, Y. Do I see those 4 together somewhere? Here's A, here's C, here's F, and here's Y. So they are all the same elements, and they are in the same order. So yes, R is a subsequence of S. What about T? So T, I have B, A, and Y. Let me erase this. So I see I have B, A, and Y. I have all the right elements, but they're not in the right order. These two would need to be switched. If this was A, B, and Y, then it would be a subsequence. But since the order is not the same, it is not a subsequence of S. Same elements, not the same order. I'll write that, not the same order. Okay. Next one is the sequence 2, 4, 8, 16, 32, dot, 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 2k, 2 to the power k, dot, dot, dot. So this goes on forever. And is that a subsequence of 2, 4, 6, 8, all the way up to 2k and beyond? So this is the sequence that we're going to be looking to see. Are all of those elements in here? If I'm looking at this sequence, I'm seeing that all of my numbers are positive. They are all positive. They're all integers. They're all even. 2k means they're all even. And if I'm looking at the order, they're in numerical order. So let's go see, does this sequence over here meet all that criteria? They are all going to be positive. They are all even. This is doubling, so I'm missing a bunch of even numbers, but that's okay. But all of these are going to be even. They're all going to be integers, and they are in numerical order. So yes, this to the power 2 to the power k is a subsequence of 2 times k. Okay, let's look at example 3. Define a sequence S by S sub n equals 2 to the n plus 4 times 3 to the n, where n is greater than or equal to 0. Well, let's take a look at A. All right, here in A, I want to find S sub 0 and S sub 1. For S sub 0, that's 2 to the 0 plus 4 times 3 to the 0. Non-zero integer to the 0 power is 1. So 1 plus 4 is 5. First element in my sequence is 5. S sub 1, let's see, 2 to the 1 plus 4 times 3 to the 1 is 2 plus 12, that's 14. All right, so that's A. I found the first two elements of the sequence. Let's take a look at B. Find S sub n minus 1. That's 2 to the n minus 1 plus 4 times 3 to the n minus 1. And S sub n minus 2 is 2 to the n minus 2 plus 4 times 3 to the n minus 2. Okay. Next up, part C, I want to show that S sub n is actually equal to this. 5 times S sub n minus 1 minus 6 times S sub n minus 2. Okay, well, let's look at left-hand side and right-hand side. The left-hand side is 2 to the power n plus 4 times 3 to the power n. That's what S sub n is. And I want to work with my right-hand side and try to turn it into that. So I'm going to use some algebra here. A lot of rules of exponents going to come into play. 5 times, I actually know what S sub n minus 1 is and S sub n minus 2. I was asked to do that in part B, so I'm going to fill those in. 5 times 2 to the n minus 1 plus 4 times 3 to the n minus 1 minus 6 times 2 to the n minus 2 plus 4 times 3 to the n minus 2. Let's see, I'll do a little bit of distribution here. That one and the negative 6. So this is 5 times 2 to the n minus 1 plus 20 times 3 to the n minus 1 minus 6 times 2 to the n minus 2 minus 6 times 4 is 24 times 3 to the n minus 2. All right, now here is where the magic happens. So this right here, 2 to the n minus 1 is 2 to the n, is 2 to the 1 times 2 to the n minus 2. Because when I multiply two things with the same base, I add the exponents. So 1 plus n minus 2 is n minus 1. So I'm going to rewrite this term using that, and I'm going to also do the same thing to this term, except it's going to be with 3's instead of 2's. So I'm going to have 5 times 2 to the 1 times 2 to the n minus 2 plus 20 times 3 to the 1 times 3 to the n minus 2. And the reason I'm doing that is because these terms over here have 2 to the n minus 2 and 3 to the n minus 2. And I want to be able to combine some like terms here. Minus 6 times 2 to the n minus 2 minus 24 times 3 to the n minus 2. Okay. So now what I can do is I can combine the 5 in this 2 and the 20 in that 3. And I get 10 times 2 to the n minus 2 plus 20 times 3. Oh, sorry, 20 times 3 is 60. 60 times 3 to the n minus 2 minus 6 times 2 to the n minus 2 minus 24 times 3 to the n minus 2. And now I've got some like terms that I can combine together. I've got this one with 2 to the n minus 2 and that one. So that is going to be 4 times 2 to the n minus 2. And then I have, let's do another color, orange. I've got this one and that one. So 60 minus 24 is plus 36 times 3 to the n minus 2. All right, so let's check in and see where we're headed. This is what I'm aiming for. I'm shooting for this. So I want to have 2 to the n and 3 to the n. So I'm going to do another rewriting with my exponents step. Let's see. Let's do, I guess I'll do purple. Okay, so this is going to be, I'm going to rewrite this 4 as 2 squared times 2 to the n minus 2. That way I can have the same base. And I'm going to do the same thing over here. Let's see, 3 squared is 9, and 36 divided by 9 is 4. So I'm going to do 4 times 3 squared times 3 to the n minus 2. And now I can combine these together, that with that, and also this with that. So this is, there's nothing left out front here. I'm taking that whole 2 and putting it up there. So there's just a 1 left. That's just 2 to the n plus, and then I have a 4 left here, and then this is going to get added to that, and I'm going to have a 3 to the n. So now I have 2 to the n plus 4 times 3 to the n, and that is my left-hand side. So that was a lot of algebra, a lot of exponents, rules of exponents, but I have showed that this right-hand side is equal to my original sequence. Okay, let's talk more about sequences. Sometimes it's necessary to find the sum or a product of consecutive terms of a sequence. Either you can add a certain number of items. You can leave that number of items arbitrary, like by leaving it as an n, or you can specify a certain number of indices that you want to add together. But here is the one for sum using sigma, and here is the one for product using a capital pi. And you can see the difference here. These are all sums, adding, and these are all multiplication. So let's take a look at some of the things we can do with these sequences. Example 4. Let A be the sequence defined by a sub n equals 3n for n greater than or equal to 1. And I want to find the sum from I equals 1 to 4 of a sub I and the product from I equals 3 to 5 of a sub I. Let's see. So it might be helpful to know what is a sub n. What are some of the elements of a sub n? Let's see. A sub 1, a sub 2, a sub 3, etc. So a sub 1 is 3 times 1, which is 3. And then a sub 2 is 3 times 2, which is 6. A sub 3 is 3 times 3, which is 9. And now I'm seeing I'm just going by 3's. 15, 18, etc. So that is my sequence. That's going to help me figure out what am I going to be adding and what am I going to be multiplying together. So the sum I equals 1 to 4 of a sub I is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. I'm just adding those four elements together. And I actually very helpfully made this list over here. So this is going to be, first one is 3. 3 plus 6 plus 9 plus 12. Add all those together and you get 30. Let's do pi. The product of I equals, whoops, sorry, not 1, I from 3 to 5 of a sub I is a 3 times a 4 times a 5, which is, let's see, 1, 2, 3, which is 9 times 12 times 15. That's a lot of numbers. 9 times 12 times 15 is, insert calculator, punching noises here, 1,620. Sometimes we are going to be adding n number of terms, and we might like to know some patterns that we can recognize. So here are some formulas. The sum of k equals 1 to n of k is equal to 1 plus 2 plus 3 plus 4 plus 5 all the way up to n is this right here, n times n plus 1 over 2. And I can prove this using mathematical induction. I'm not going to do that now, but that could be done. We talked about induction in section 2.4. The sum of k squareds is this thing right here, and the sum of k cubed is this thing right here. So we can use these when we're trying to write an explicit formula for something with n's in it or with some sort of variable in it. We don't want to have any dots in our formula. We want to be able to use this right-hand side. So we're going to see if we can recognize any of these patterns, and then we can use some of these formulas. All right, example 5. Let sequence b sub n be the quantity -1 to the power n times n, where n is greater than or equal to 1. So it's a good idea to kind of figure out what is this sequence look like. So let's see, some of the terms of my sequence are going to be -1 to the 1 times 1, and then -1 squared times 2, and then -1 cubed times 3, and then -1 to the 4th times 4, and then etc. So let's see, this is going to be -1 times 1 is -1, -1 squared is going to be +1, times 2 is 2, and then this cube is going to stay negative, and then so I'm going to have a -3. This is going to be positive, and then 4. So it looks like I am going up 1, 2, 3, 4, but I'm alternating negative and positive. So -5 and then +6, -7 and then +8. I'm recognizing that's the pattern of this sequence. I could do some more terms if I wasn't sure of the pattern yet, but I think I have enough terms to figure that out. All right, so that's what my sequence is looking like. I want to find a formula for c sub n, which is where I add up all of my b sub i's from I equals 1 to n. And I want to figure out what this looks like, adding up all of these. And I think it's probably going to depend on whether or not what n is, if I'm stopping at an odd or an even number, because that odd or evenness is a defining feature of this sequence. So let's take a look at two different cases. Case number 1 is if n is even, then n could be written as 2k. And then c sub n is going to be -1 plus 2 plus -3 plus 4 plus ... plus something, and then plus my last term, which is going to be 2k, because I said n is going to be an even number, so let that be 2k. So this is going to be 2k minus 1. Whoops. So I'm filling in the second to last term at the end. And so now as I'm examining my sequence, I'm seeing that these two add together. 1 plus 2 is +1. These two add together. -3 and 4 is +1. So all of these copies in here are going to add to -1. And then my last two, 2k minus 1 plus 2k. Oh, this is oops, I made a mistake here. This is going to be, since this term is positive, this is actually going to be negative. So this is -2k plus 1. So adding these terms together, and I get a +1. So how many pairs of these +1s did I get? I got k of them. I'm doing this k times. K copies where I'm of 1 that I'm adding. And I know from over here, if I divide both sides by 2, that k is equal to n over 2. So however many numbers I added together, I smashed 2 of them together to get 1. So that many numbers divided by 2 is going to be how many times I'm doing this. So k is n over 2. So my sum is going to be n over 2 if n is an even number. Let's look at if n is odd, then n equals 2k plus 1. One more. And then c of n is going to be -1 plus 2 plus -3 plus 4 plus ... plus negative 2k plus 2k minus 1 plus 2k plus negative 2k plus 1. And I already know something about this whole sequence. This is all n over 2. I mean, this is all k. There's k copies of 1. This was 1 plus another 1 plus all the way up to this plus another 1, and we did that k times. So that is k. So then I just have this last little bit over here. So this whole thing is k minus 2k plus 1, which is k minus 2k minus 1, which is minus k minus 1. And I know from over here, I can figure out what k is. So n minus 1 equals 2k, or k is n minus 1 over 2. So I can use a little bit more algebra over here. Negative n minus 1 over 2 minus 1. I can combine these together. Let's see. This is negative n over 2 plus 1/2 minus 2 over 2 is going to be negative n minus 1 over 2, which is negative n minus 1 over 2. So, oopsie, plus 1 over 2. I took out both of these negatives. So this is my answer for this side of the sum. Negative n plus 1 over 2. All right, that was sum. Let's get product. I want to find a formula for d sub n, which is the product I equals 1 to n of d sub I. So let's write down what this is. It's negative 1 times 2, and then negative 3 times 4, and then all the way up to negative 1 to the n times n. Let's see. And that's going to be a little bit hard maybe to do something with. Because I don't know how to interface with this. So I think I might actually not write it like this. I might go back to writing it with the exponents on these terms over here. So let's do negative 1 to the first times 1 times negative 1 squared times 2 times negative 1 cubed times 3 times all the way up to negative 1 to the n times n. And now I'm seeing I've got all of these negative 1s with exponents. So I can add all of these exponents together. So I've got negative 1 to the 1 plus 2 plus 3 plus 4, etc., all the way up to n. And then I have 1 times 2 times 3, etc., all the way up to n. There's your times in here. Well, this is a sequence that we could recognize. We probably maybe don't recognize it yet because we haven't had a lot of practice, but I'm going to scroll back up here, and that is this sequence, 1 plus 2 plus 3 all the way up to n. That is n times n plus 1 over 2. So that's what I'm going to write over here. The sum of k equals 1, from k equals 1 to n of k is n times n plus 1 over 2. And that's going to be what that exponent is. So that's part of it. And then this right here, 1 times 2 times 3, etc., all the way up to n, that is n factorial. So this is going to be negative 1 to the power n times n plus 1 over 2 times n factorial. And that is my formula. When you're writing a formula in this section, what you want is you want to write it in such a way that I don't have any ... dots. So here, all of these steps, I still have the dot, dot, dots. And I want to be able to write my formula in such a way that I don't have the dot, dot, dots anymore. Okay, ready to transition to something a little bit different, and that is strings. Strings are used a lot in programming, and in programming, a string is a sequence of characters. A string sequence of characters like this one. The Beatles is a great rock group with quotes. That's a string. The double quotes mark the beginning and the ending of a string. Strings can contain letters, they can contain lowercase, uppercase letters, they can contain spaces, they can contain certain characters. It depends on kind of what language you're in, if you're programming, with what that language will allow, but they can often contain characters, they can contain numbers as well. So a string over X, where X is a finite set, is a finite sequence of elements of X. So here where you're gonna there are special ways that strings, there are special strings and ways of describing strings, goodness. Let X be the set A, B, and C, so I can make a whole bunch of different strings if I'm allowing these characters to be in my string. First special string is this one, and that is the Greek letter lambda, and that is the empty string, also called the null string. And that is, the empty string. You can write it as the empty set or like that, but that is the empty string. Here's another one. I guess this should probably be another bullet point. AAB is a string over X because it's using elements from X. A3B C4B is a shorthand for 3 A's and then a B and then 4 C's and then another B. And that is also in X star, where X star denotes the set of all strings over X. Oh, I guess I skipped one. I went out of order. So, sorry, back to this one. X star denotes the set of all strings over X, which there are an infinite number of those. And the null string lambda is included in that X star. And this is also included in that X star. And so is this one right here. The length of the string is the number of elements in the string. And to denote that, we use the same thing we did for cardinality, the vertical bar on either side. So we have a couple of examples to work through here. In example 6, if alpha is equal to A, B, B, A, B, C, 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 then the length of alpha is 1, 2, 3, 4, 5, 6, 7, 8. And the shorthand is A, 2 B's, another A, another B, and 3 C's. AB squared, ABC cubed. If alpha is CC, ABCC, and beta is B, A12, C3, B2, C3, then what is the length of each of these strings? 1, 2, 3, 4, 5, 6. Length of alpha is 6, and length of beta is, 1B plus 12C plus 12A's plus 3C's plus 2B's plus another 3C's. That is 21. Different programming languages will have different ways to find the length of a string. That is a very useful feature that hopefully, if you have not learned about that yet, you will someday. How can we join strings together? That is with concatenation. Is the operation of joining character strings end to end. For example, the concatenation of snow and ball would be snowball. In example 7, if alpha is equal to AACCBCC, and beta is C squared, B squared, A cubed, what is the concatenation of A and B, which we denote as, of alpha beta, which we denote as alpha beta? So alpha beta is A, which I'm going to write this as A squared, C squared, B, C squared. A squared, C squared, B, C squared, and then another C squared, B squared, A cubed. So this part is alpha, and this part is beta. Well, but it looks like in this middle, I've got some C's kind of at the end of alpha and at the beginning of beta. I can actually combine those together, and I should combine them together. This is A squared, C squared, B, C4, B squared, A cubed. Let's take a look at beta alpha, which is going to be different from alpha beta. Beta alpha is C squared, B squared, A cubed, A squared, C squared, B, C squared. And again, I've got this middle combination that I can combine together. And to get, oops, I changed the order of my pens. That was kind of an accident. Oh, now I can't figure out how to undo that. Well, c squared b squared a 5. 2 plus 3 is 5. C squared b c squared. Okay. Last page. A string beta is a substring of string alpha if there are strings gamma and delta such that alpha equals gamma, beta, delta. And it says here that gamma and beta may be an empty string, maybe the empty string lambda. And also it says that alpha can be a substring of itself. So here is my string beta. And if there could be something before it, or something after it, or something on both sides, or neither, and that would all be a substring. If x is equal to the set ABC, and A is in x star, which again, x star was the set of all strings over x, alpha to the power capital R denotes alpha in reverse order. An example 8, let alpha be A, CCB. What is alpha reversed? Alpha reversed, oops, I said alpha to the beta. Alpha reversed is B, C, C, A, or I could write it as B, C squared A. B, this is beta. Is alpha a substring of beta? Let's see, alpha is A, C, C, B. Do I see A, C, C, B anywhere in there? I see, no, I don't. Not in that order. So alpha is not a substring of beta. What about alpha reversed? Alpha reversed is BCCA. Do I see that anywhere? Ooh, I do right there. BCCA. So alpha reverse is a substring of beta, where gamma, the thing that comes before beta, is all that stuff. And then delta, the thing that comes after beta, is just B. So this would be gamma, and this would be delta. So this one, yes. A substring. Last one, C. Gamma is A, CC, B, CCA. Is alpha a substring of beta? Oops, this is supposed to say gamma. How about alpha reversed? All right, so alpha was ACCB, and there's ACCB. So alpha is a substring of gamma. What about alpha reversed is BCCA? Oh, that is also a substring. Here it is, BCCA. Alpha reversed is a substring as well of gamma. Oops, got my F and up. Check. Okay, and that is the end of this section. I will see you next time.